Alright, so today we're continuing with sort of advanced visual perception, and we're going to talk about depth perception today. And a lot of what we're going to talk about goes back to one of the last things that we talked about last week, which is the inverse projection problem. What was the inverse projection problem? Yeah. No, it does have the word inverse in it. And it is about the image on our retina, but it's not that it's flipped upside down. No? Nobody? All right, it's that the image on our retina is two-dimensional, right? And multiple different images, multiple different things in the environment can result in exactly the same stimulation of the retina, exactly the same stimulation of the retina. So how do we figure out if, I'm looking at a small circle that's close to me or a large circle that's far away, if that circle makes the same image on my retina, right? And so this is one of the challenges of depth perception. So the viewfinder has, if you take out the disc and look at it, each image on there, there are two of them, and one's projected to your left eye and one's projected to your right eye, and those images are slightly offset so that they're creating what's called binocular disparity. And binocular disparity allows us to see in three dimensions. So I'll come back to this when we get to binocular disparity. All right, so let's put it this way. So to start out, we're going to talk about, so we have a whole bunch of cues or heuristics that help us do depth perception. Some of those are going to be what we call monocular cues, meaning you can perceive depth with only one eye. You don't need both eyes in order to perceive depth. Then we have some ocular motor cues, which means how our eyes move is a signal to our brain about what we're looking at, how far away something is. And then what we'll spend most of the lecture talking about is the fact that because we have two eyes, and because the image in our left eye and the image in our right eye are slightly different, right, as they are with the viewfinder, right, that generates depth perception, or three-dimensional perception. All right, so let's start with monocular cues. All right, so here's the most embarrassing picture I could find of my kids 20-something years ago. Right over 20 years ago. And so, if you look at this image, right, what are some of the things that we've talked about in terms of visual perception? What did we talk about last time? Color. Okay, so there's different colors represented. Are you doing figure ground separation? Is there a figure in the background? Right? Okay. So what are some of the cues that allow you to know that there's a figure in the background? Sorry, my batteries are out. All right, how do we tell that something has depth? How are you perceiving that there's depth in this image? Right? Because it's not, it's flat. But you perceive there's depth. Why do you perceive there's depth? What's in the forefront of the picture? What's closest to you? Kids, right? And my daughter, is she in front or behind my son? Why? What's that? because of what we call occlusion, right? She's covering up some of that. And they're in front of this rail, and there's a boat back here, right? How far away is that boat from them? What's your guess on the depth perception? How far away is the boat from the stairs? Someone give me a guess. How many feet away? 6 feet away? Okay. And so how big a boat do you think that is? 10-foot boat. Okay. And then how far away is the water from everything? 25 feet, right? All right. So this is just like a cheesy backdrop from Walmart. Right? They're not really sitting on a porch with a boat and all that. But we have cues, pictorial cues, binocular cues, that tell us, hey, this boat is about 6 to 8 feet away from the bottom of these steps, right? And we have those cues because of where it's located, how high up it is, and how relative big we think the boat is. All right, so occlusion is a learned cue. If something is covering something up, and the thing that's being covered up is behind the other thing. And we have binocular cues that are learned. Sometimes these are also called pictorial cues because they can all of these cues help us perceive depth in a two-dimensional image, in a picture. All right, so over here, which of the three clouds is furthest away? The one on the left, the one in the middle, or the one on the right? The one on the left, okay? What about, so why do you say that?
It's the smallest.
It's the smallest, okay? Well, the three people on there are all the same size. Which one is closest to you? The one on the left, the one in the middle, or the one on the right? How many people vote right? Why? It can't be size, right? At the bottom of the page, right? So we have a cue called relative height. Again, these are heuristics. These are rules, shortcuts our brain uses to help with depth perception. The relative height heuristic says if something is above the horizon, the closer it is to the horizon, the lower it is, the further away it must be. Size also matters. So you're assuming that these clouds are all about the same size, that this isn't a tiny cloud. So if these clouds are all about the same size, you have both size and relative height over here, right? If below the horizon, objects that are closer to the horizon are further away. Objects that are lower in the horizon are closer to us, right? And so here, it feels a little unnatural because you would assume if this is the closest one, and these are getting further away, that they should also be getting smaller in size. And so when those heuristics conflict, it feels like someone drew the picture wrong. All right. So again, which rabbit is closest to us? The one all the way on the right corner, even though it's the smallest rabbit up there. Right? But we know rabbits can have different sizes. Which rabbit is furthest away? The one in the middle? This one? Right? So again, smaller size and higher in the picture tells us, hey, this one is sitting further away than these are. This down here is baby rabbit. Right? Because we reconcile the fact that, hey, The relative height is can be a stronger cue than size. So how do we then rectify the size? We're like, well, that's just a small rabbit compared to this rabbit. All right. So depth and size are totally linked together, right? Here, right, what makes you feel uneasy about this picture? Or do you feel uneasy about this picture? Does it look right? No. Why doesn't it look right? Because the biggest car is furthest away. And we have occlusion, and we have relative height telling us that these cars are parked closest and furthest away, yet size is conflicting. And we're like, how can this be a tiny car and this be such a big car, right? We're perceiving, because our depth perception is so strong from relative height and occlusion, our brain is saying this must be a huge car and this must be a tiny car. All right. Again, all of these are monocular cues. Okay? If we look at this, right, we have the center object is closest, followed by the base, followed by this glass, right? And we have occlusion, and we have relative height telling us these things, right? Now, what about now? Which one is closest to us? What do you want to say? Based on occlusion, you want to say that the flower base is in front of this. Occlusion is very strong. If something is occluded, it has to be behind it, right? But what's conflicting with that? The relative height, right? The relative height. Can we resolve that? What about now? You're like, okay, it's floating in air. I don't really know how it's floating in air, but adding that shadow says, yep, that's in front of that. Right? Relative height is no longer conflicting. All right. Same thing here, right? Who is in front of who? Who is the closest? The brother or the man standing there? What about if, right, we add shadows, right? So here with relative height, it looks like even though she's slightly bigger than the older man, relative height says she's about to pass it, right? But as soon as we add a shadow, it rectifies that and we're like, okay, she's jumping or running and she's actually passing it. All right. Again, so now we're starting to get into this idea that size is a perception. So we have actual retinal size. What is the image on my retina? What is the actual size of the object? So here we have a golf ball, a baseball, and a basketball. All things that you know are very different sizes. But on the retina, they're stimulating exactly the same amount of space. They're exactly the same size on the retina because the basketball's further away. Right? Again, relative size and relative height can tell us, if we look at this picture, you see the biggest tennis ball, even though it's higher up, appears closer than the smaller one. Because we know that all three of these things are the same size. Therefore, if we're not perceiving them as the same size, they must be different distances away from us. Because we know that distance and size are related. Even though relative height would say that should be closer, the fact that the size is different overrides that. kind of like the occlusion overrides the building. All right, some more monocular cues, right? How far away is this building from where we're standing at the Varsity in downtown Atlanta? Is it across the street? No. How far away do you think it is? A couple blocks away, right? And why do you say that? Why don't you think it's right across the street? A different shade, right? The clarity of this is different than these trees that are right across the street, right? So the more, just like we talked about with color, the more atmosphere we have in between us and an object, the more light gets scattered and it starts to appear bluish, which there is sort of a bluish tint to this, right? The more atmosphere, and really that's probably 4 or 5 blocks away, but there's so much smog in downtown Atlanta, there's a lot of particles in the air, and so there's a lot of atmosphere interference or perspective, right, that happens. Again, monocular cues. These are all monocular cues. So we can take this image here that doesn't really have very good depth perception with it, but if we shade it like this, where these are lighter color and then darker color, now we've added depth perception to that. Because we assume that these are all similar types of objects, these must be further away. Therefore, they also must be bigger than these. Linear perspective is a monocular cue that says the further away things become, that they converge to a focal point. So in this picture, the focal point is back here, and these lines converge, everything up here converges, everything is converging to where that tree is there, right? In addition to linear perspective, we also lose the ability to see texture. So up here the tiles are nice diamond shape, they start to become flatter with linear perspective, and then all of a sudden we lose the ability to see that gradient. The further away something is, the less clear it becomes, the harder it is to see that gradient. All of these things are cues that have to agree with one another in order for us to perceive this as a well-done picture, right? Why did the pictures that my kids drew in kindergarten not look like this? Because they didn't understand linear perspective and texture gradient and all of those cues. Occlusion. Okay. Again, here's 2 other examples. On the review points, I put to figure out the Ponzo illusion on your own. It's in the textbook, but it has to do with converging lines with linear perspective. Right? We also here see texture gradient. You can see the railroad ties here, but as it gets further away, the railroad ties become blurred until we lose that. They become denser and we lose that ability to see. Right? I mean, an actual photograph here, right, of something with depth, as opposed to something someone has drawn. Again, here, the denser these become and the smaller they become, as they approach what appears to be a horizon, they appear further away. All right. Texture gradients are important. They provide us information about how far away something is. And if we take away our texture gradient, right, so you're standing on a ledge, and there's a target over here, right? Do you think if we remove the texture gradient, depth perception becomes less accurate? In what way do you think it becomes less accurate? if I ask you to judge how far away the target is, are you gonna, if you're not gonna be accurate about it, are you gonna underestimate or overestimate how far away that is? What do you think? In what way does our brain err? Well, if I told you you had to jump across that, right, what would you want to do? If you're trying to figure out how to jump across this thing. Yeah, you'd want to overestimate, right? You wouldn't want to underestimate. You end up here. So when we take away, when we have texture gradient, there's no gap, we're really good at estimating how far away something is, right? If I'm looking at the floor here, and I know to there, okay, that's about 6 feet, right? Take away that texture gradient, I'm going to think that's longer than 6 feet, and that's a safety thing, right? Because if we have to jump over that, we want to overestimate so that we can make sure that we can do that. Okay. So, we also have some movement-based monocular cues. So everything we've done so far is static, meaning it can be represented in a picture, right? Static monocular cues. Motion parallax says that objects that are closer, as we're moving, objects that are closer appear to move faster than objects that are further away. And so, you've experienced this riding in a car, right? You're riding in a car, the signs and the things on the side of the road are going past really fast, but you're looking out and there's a farmhouse out there and it's just going kind of slow, right? Things that are further away move slower, and things that are up close move faster when we're moving at a constant speed. And this is simply because if you're in this train, right, and this is what you see, and then 2 seconds later, this is what you see, right? The flower has moved further in the same time as the cow, which hasn't moved very far at all, or the tree. Right? So how do we measure speed? If you're in your car, how do you know how fast you're going? Miles per hour, it's distance divided by time, right? Distance divided by time. So the amount of distance that something moves across our retina in the same amount of time is the speed, right? It's how we're measuring speed. And this flower has moved a further distance in 2 seconds than the cow did. So it appears to be moving faster. It appears to be moving faster, right? So here we have point A that's up close. This is where it is on my retina. Point B, if I move over here, point B has traveled that far across, or point A has traveled that far across my retina. Point B has only traveled that far, right? And so if that was in 1 second, right? A is moving 6 centimeters per second, 6 centimeters across my retina. B only moved 2 centimeters per second. So it appears to be moving much slower than A is. Everybody get that? Okay, that's called motion parallax. Motion parallax. We also, similar to occlusion, if something's moving and not static, then parts of that thing that are moving may be deleted, meaning occluded, or accreted, created, or shown, right? So if I put this yellow person walking down Fort Main, right, we know that they're on the street because of where their feet are, but also, okay, their feet are occluding and accreting the curb back here, and we know they're in front of this tree because, again, parts of the tree are getting occluded and shown. If I put a person back here, right, because none of this tree is being accreted or deleted, right, we know exactly where that person is. So when we add movement, right, the fact that parts of the picture are being included and not included, which is what we call accretion and deletion, right, gives us that depth perception. It lets us know where our objects are relative to each other. Where objects are relative to each other. So, accretion and deletion and motion parallax, two movement cues, depth cues, that we have to have movement in order for those to work. Yes, sir. All right, so far, monocular cues. Everything's been monocular. Okay? You can close one eye, okay, and still see that depth perception. If you want to know is something a monocular cue, if you close one eye, you still see the same depth perception. Now, the rest of what we're going to talk about requires two eyes. It requires us to have two eyes. All right. First of many times today, and I'm going to ask you to do this silly thing. So, take your right finger and hold it about 2 inches from your nose, and your left finger as far away from you as you can. All right, focus on your left finger that's far away, and then I want you to focus on your other finger, and I want you to feel what your eyes do. What do your eyes do? Switch back and forth between the two. Are they moving? All right, when you focus on the thing that's up close, your eyes focus in. As you look at the things further away, they move out. We can feel the amount of convergence and divergence of our eyes, and that tells us that is a depth cue for us. Okay? Right? Our eyes move in and out. The convergence of the eyes for something that's close, divergence of the eyes for something that's far away. Why do we have all these cues? Why do we have all these different heuristics? If I ask you to do this, do you have an atmosphere perspective for your second finger? No, right? So these different cues work for different depths. Atmosphere perspective is something that has to be really far away. Right? Really far away. Convergence and divergence of the eyes only is for stuff close up. Right? So if you look at the person sitting in front of you and then look at me, and then look back at the person sitting in front of you and then look at me, are your eyes converging and diverging? Not very much, right? Maybe just a little bit. They're moving because you're looking at different places, but once you get about an arm's length away, our eyes are fully diverged and they don't move anymore. So, again, 4 meters or more sort of away, and we don't have any more convergence in the eyes. Right? In addition to convergence and divergence, we're also focusing that image by squeezing our lens. So remember I talked about the older you get, the harder it is to focus on things up close. That's why you hold the menu real far away from you, or you have to put on reader glasses to magnify it, right? So that muscles contracting accommodation is another cue. And so both of these are muscle signals. These are motor cues as to where our eyes focusing. Where our eyes focusing. Something up close, something far away. So we have a bunch of monocular cues, we have 2 motion cues, and now 2 oculomotor cues for depth perception. That's it. Yeah, It's not even that you feel it. This is subconscious, right? That we're sending an output from, hey, I'm making my eyes move in. That motor output to converge your eyes gets sent to part of our depth perception area to say, hey, this must be something up close. Because you've never thought about your eyes converging and diverging before. It's not a conscious awareness thing. You can't even tell about accommodation, right? You can't consciously feel that contraction on your lens like you can when you move your eyes. All right. So we have a large overlap of our field of view, and each eye is getting slightly different angle perception, right? And so if you look at me and you close one eye and then open the next eye, I kind of bounce back and forth a little bit, and that's the difference in the angle that you're perceiving me. All right. So because these images that hit our eyes are not exactly the same, this is called binocular disparity. Binocular disparity means that the exact same image is not hitting both of our eyes. And we can use that as a cue for depth perception. So here, this is an example of if you were looking at this bike rider with your left eye, there's a different occlusion that's happening here than with your right eye. Slightly different signals, and that's exactly what is happening here in the viewfinder, is that the two images are offset to match up with your binocular disparity. To match up with your binocular disparity. So again, here's the two images, right? So this one, Thomas, there is not including this telephone pole as much. Here, you can see it's not a lot, it's just a little bit. It's including there, right? And there's slightly different things back here, right? And those cues, our brain reads them as, hey, this is a three-dimensional thing because I'm seeing it from two different angles. And the stereoscope example is, remember I said that there was the stroboscope was apparent motion, right? That Gestalt couldn't try to explain, structuralism couldn't explain. The stereoscope is where you look into, like the Viewmaster, with slightly different images and perceive a three-dimensional object, right? And there's some figures in your book that you can try this. It's hard to do it on the screen. But the Magic Eye random stare, have you ever seen the Magic Eye books where it looks like a random picture, but if you stare at it, you can generate a three-dimensional image that's hidden in it? There's some of these in your book as well, right? All of that is utilizing binocular disparity to generate three-dimensional images. These are called random dot stare. All right. So some of this is a lot easier to demonstrate with video than it is with static images. All right.
Hey, Vsauce, Michael here. This is called the Dolly Zoom effect, and the optics that make it possible are also responsible for what's called the moon terminator illusion. A terminator is the line between an illuminated and dark side. Light arrives perpendicular to the terminator, but it doesn't always appear to. Maybe you noticed this before. When the moon and the sun are up at the same time and a good distance apart in the sky, the direction the moon is being lit from won't always appear to line up with the position of the sun. What's going on here? The answer lies in visual angles. The further away from you something is, the smaller it will appear to be. In psychophysical terms, its visual angle shrinks, the angle within your field of view that it stretches across. Now, this means that everything we look at is foreshortened. That is, it diminishes in size towards the horizon line, a line infinitely far away. Things that far away are foreshortened to the point at which they have no height whatsoever. This distortion affects everything that we look at, but it doesn't confuse us because our brains know about it. We can look at an object that is foreshortened and figure out what it probably actually looks like. For example, a door is a rectangle, but it's rect by foreshortening when open. Closer distances appear larger. The whole shape is different, but your brain isn't freaked out every time a door opens because it understands that different sensations don't necessarily mean different actual things. It's called subjective constancy. Our brains cleverly factor in previous experiences and perspective clues from the surrounding world to calculate in real time whether changes in what we sense are because of actual changes in the things we're looking at or are just merely products of their positions or the surroundings.
All right, so this is really important when he's saying some of these demonstrations that he's doing, right? So our brains learn the heuristics. This is a developmental thing. Very young kids are not good at this, right? They have to have enough experience that the brain learns to ignore these changes, right? That when a door opens, right, that it maintains its shape constancy, even though our vision is telling us something very different.
For example, I, right now on this video screen, am vulnerable to foreshortening, but I probably look okay to you. However, if we frame in really closely and remove surrounding perspective clues, I can be made to look weird, strange, a little scary, distended. I'm foreshortened without the necessary tools around me for you to mentally adjust. This is probably the crux of the moon terminator illusion. Take a look at this. The line where that wall meets the ceiling is a straight line. Seriously, take a look. If you look to the left and right, it continues to look straight. And trust me, this building was built with level, straight ceilings, but that's not what your eye senses. A camera will help demonstrate this. It doesn't add in the post-sensation processing that our brains do, and we can also frame in to remove other clues telling us what to think. Now, sure enough, right in front of us, the line is level with the screen of the camera. It's a straight line, but if we move our eyes across the line, look what happens. If I pan this way, the slope changes, and now the line appears to be going up and to the left. And if I pan this way, the line appears to be moving up and to the right. What's going on here? A straight line can't have changing slope. That's what a curved line does. Just like the curve we think we see between the sun and the moon. But wait, if the line between the sun and the moon is curved because of foreshortening, why don't we see lines like this one as curves? Well, here's the clue. Clues. We know what rooms are supposed to look like. We know how they're built. We have experience with them. And there are other things in the environment helping us. But when you look at the sky, there's not much to help you. In the absence of clues about distance and perspective, our brains assume that whatever we're looking at is equidistant from us, making the sky a sort of dome surface, like a planetarium screen. The only clue we have then is the horizon, but it's a red herring, because the horizon doesn't foreshorten. It's just a place where, due to foreshortening, everything becomes infinitely flat. Brian Rogers and Olga Naumenko demonstrated that these things result in the Terminator illusion by using a planetarium. They projected 2 dots onto its dome, mimicking our perception of the sun and the moon. They then asked participants to place a 3rd dot on the straight line connecting them, but But just as in the Moon Terminator illusion, people incorrectly placed the third dot. They were influenced by a desire to stay parallel to the horizon, as if it was subject to the same foreshortening rules. Our brains also often fail to factor in foreshortening when it comes to crepuscular rays. Light beams streaming through gaps in clouds. They appear to converge from a common point, as if the sun is only a few thousand meters above Earth. But of course, in fact, the sun is extremely far away, and these lines are actually pretty much exactly parallel. It's true. They look like they converge for the same reason railroad tracks appear to converge. The visual angle of the distance separating them shrinks the further down you look.
Grammarly now uses AI to help you write, not just revise. Type of ground to...
Sometimes our brains do the opposite. They assume and consider foreshortening even when it isn't really there. Like in this illusion, where the cars seem to be different sizes, but in actuality on the page are all the same size. Everything else in the image is affected by foreshortening, so our brains assume that the cars are too, and decide that in order for them all to have the same visual angle, which they do, the more distant ones must be literally larger in real life. The rate at which the visual angle of something you are looking at changes as you move toward it or away from it is not constant. In order to cut the visual angle of an object in half, its distance from you must double. That means objects really, really far away require a lot more
This is
movement
motion
to have their
parallax,
visual angle
moving
change
faster
compared to nearer
than the things in the back.
This is
moving
called
slow.
parallax, and it's a major reason moving allows us to learn so much about depth. It's why stuff on the side of the road whizzes by you as you drive past, while distant features of the landscape appear to only crawl past. A really distant thing, like, say, the moon, 384,000 kilometers away, appears to move so little as you do, it can seem to be following you. It's not, of course, it's just geometry. For the same reasons, moving a camera through space will affect the visual angle of nearer things, like the Vsauce mud here, much more dramatically than distant things, like Jake Chudnow's album Against the Wall. It is barely changing size as we move back and forth. But unlike moving, zooming increases the visual angle of everything equally, regardless of depth. Notice that when zooming, the distant album grows and shrinks right along with the mud. Now, if you move in while zooming out, or vice versa, the zoom will be most apparent when looking at distant things, while the move more apparent on near things. The result can be trippy. Here, I've been placed where both effects cancel each other out, so everything around me changes instead. Another great illusion that takes advantage of parallax is the popular star field or hallway illusion. Cover the middle of the video, and you'll appear to be moving much faster. But if you cover the edges, you'll appear to be moving much slower. All you're doing is altering the perspective clues your brain receives about movement. The nearer stuff at the edge changes position faster than the distant stuff way ahead. So if you cover the slow distant stuff, your brain only has the faster moving stuff to judge speed from. But cover the faster near stuff, and the slower stuff becomes the new near. Your brain assumes that you've slowed down. The optics and mathematics behind all of these effects were understood at least thousands of years ago. During the Renaissance, artists used that knowledge to produce paintings that imitated reality really well. I mean, the perspective is quite realistic. But the Renaissance? Why did it take so long for us to get there? I mean, look at this pre-Renaissance painting. What the heck is going on here? The perspective is all wrong. That's not at all what such a scene would actually look like. Artists and viewers contemporary to works like that saw the world just like we do. They saw foreshortening and couldn't help but see it. Foreshortening is right there in plain sight. No, foreshortening is plain sight. So, what gives? Were medieval artists all just a bunch of 5-year-olds? No. No, in the sense that the question, is wrong. Realistic-looking perspective was used way before the Renaissance. Now, it might not have always been mathematically formal perspective, but foreshortening was understood. Western art went from this to this, not because humans all of a sudden became smarter, but because of a difference in desire. What to us today might look unrealistic and thus bad, was in its time deliberate and popular. The shift to imitating the world mathematically, as if seen through a window, was more about cultural interests in objectivity and the individual than it was about artists all of a sudden becoming smarter. Furthermore, perspective illusions show us that what we think we see isn't always what we're seeing. A child's drawing may seem crude in terms of objective mathematical imitation, but there are other things about the world and our experience of it worth imitating. Teasing out the less plainly obvious to show something personal is sometimes even harder than following perspective grids. Picasso put it this way: "It took me 4 years to learn to paint like Raphael, but a lifetime to learn to paint like a child." And as always, thanks for watching.
All right. So you can go print the slides and measure these and see that they are exactly the same size, retinal size, but our perceived size is influenced by occlusion and relative height. Right? Occlusion and relative height. So it becomes tricky then, right? How do we know what the actual size of something is? Right? And so conditions where you don't have cues, like when he was doing that star field thing and covering up the slow parts or the fast parts, influences our whole perception. The same thing here. If you don't have depth perception, if you don't know how high up you are in the helicopter, a brick or a toy dump truck, right, that's a few feet away may look like a dump truck that's 50 feet away. And why is that? What do these dot dash lines represent? You saw us talk a lot about it. It's our visual angle, the visual angle. This is the same visual angle for something 12 inches up close and something 20 feet far away. That's the inverse projection problem. Both of these images are identical on our retina. We need other cues, we need other clues in order to accurately know their depth and size, in order to know how far away they are on their size. Right? All of this is based on visual angle. All right. So again, this is the inverse projection problem. All of these ovals getting bigger and getting further away are in the same visual angle and create exactly the same image on the retina. So how do we know that this one is closer and this one's further away? We need other cues. And movement, the fact that just small movements of our eyes, right, can tell me if something's closer or far away based on how much it moves. And how much it moves. Right? So when you look up in the sky at the sun and the moon, right, do they appear to be about the same size? If you take a picture, look at them in the picture, yeah, sun and moon about the same size, right? If you look like in an eclipse, what happens? I remember the eclipse like 8 years ago. Yeah. So what happens in an eclipse? The moon covers up the sun. They're the same size, right? It fully covers it up, right? Same perceived size, right? Because they have the same visual angle. when in fact the moon is only 2,200 miles across, the sun is 865,000 miles across. It's also 93 million miles away, right? Much bigger, much further away, same visual angle, so we perceive them as being the same size. Because our brains don't have a heuristic for how do I tell the difference between 245,000 miles away and 93 million miles away, right? We don't have any other clues to tell us, let us know how far away something is. Does the moon always appear to be the same size? Or the sun for that matter? No, when is it bigger or smaller? Okay, so yes, but a full moon, right? Right. So does this moon appear to be bigger or smaller than this moon? Smaller, even though it's not full, but we can see its size, right? Exactly the same size. Right? Why does the moon appear bigger here? What's present in this image that's not present here? Cues, right? We have the horizon. We know how far away the horizon is. Here, it's hard to tell. We don't have the horizon. We don't have any other cues, right? So, again, if we give other cues, then this becomes, our perceptions are different, right? So, if you ever, the next time that you see the moon and it's low on the horizon, you can think about it. If you take a picture of it and then wait until the moon is high up in the sky and take another picture of it, and then measure, the size of the moon will be exactly the same in both pictures, but your perception that it was much bigger when it was on the horizon is because of all these other cues. So the moon doesn't change size, the sun doesn't change size. When does the sun appear really big? Sunset and sunrise when you have the horizon as a cue. Right? The sun doesn't go from being this big to being this big on the horizon when it's 93 miles away. I mean 93 million miles away. Right? All right. So we call this is that foreshortening that Vsauce was talking about. We call it the flattened heavens illusion. It means that the same visual angle, moon hasn't changed its size, right? But because of the cues, we know how far away it is. We guess that it's much further away when we have the horizon. Therefore, it must be much bigger. And up here, when we have no cues, right, we're relying solely on the visual angle, and it appears smaller. It actually appears closer to the actual size. Here, we perceive it as bigger because we think it's further away because it's behind the horizon. All right. So again, all of this gets at that inverse projection problem. Big problem, right? Talked about that. Okay. So there's actually a calculation that we can do, right, that allows us to figure out perceived size, right? So if I take my retinal image, right, how big is that image on my retina? And I multiply it by how far away that thing is. And then you can ignore K as some constant. Ignore that. Then you get perceived size. And D is perceived distance. So think about it. The moon doesn't change. The retinal image is the same in both of these places. So that number stays the same. What changes is that here, because of the horizon, my perceived distance of how far away the sun is, moon is much bigger than when it's here and I don't have any judgment of that. So in fact, when I look straight up, I'm basically just saying my perceived size is the retinal size, because I have no depth perception. When I have in-depth cues, now this number becomes much bigger, therefore my perceived size number becomes much bigger. So you should be able to explain not just the moon perceived size illusion, right, but able to explain all of these inverse projection problems with this equation. By knowing perceived distance, retinal image, multiply them, and you get perceived size. And this helps us with that size constancy, right? If I take a quarter and I hold it up really close to my eye, right, the retinal image is big, but the perceived size perceived distance is very small, because I'm holding it right in front of me. As I now make that longer, the quarter doesn't change perceived size, because now, even though the retinal size went down, my distance went up. So this number stays the same. Does that make sense? And all of this is stuff our brain has learned to do. Our brain has learned to do. All right, so how big do you think that wagon wheel is? If you had to guess, how big are wagon wheels? About this big? Yeah? What about now? No, it's like, well, how many feet tall? Like to the ceiling, 12 feet tall. Really big. Right? So what's the difference? Here, you're like, hey, brain, look up wagon wheels. How big are most wagon wheels that I've seen in my life? Oh, about yay big, right? Now we add in other cues, and we're like, hey, people don't change size. Someone could build a really big wagon wheel, but people don't normally change size. We don't think this is a 1-foot person here, right? Standing next to a 3-foot wagon wheel. Right? So, some objects that we know can't change their size very much, right, help us with our perceived size and our perceived distance. And our perceived distance. Okay.
Does what we see correspond to what's really out there? Or does our brain construct its own version of reality, one that does not always match up with the physical universe? Check me out, for example. I'm the same size here as I am over here, but over here I look much larger. No, it's not a cheap video trick, it's a trick on your brain. Here's what you're seeing. The me over here is indeed projecting a smaller image onto your retina, the region of light detecting cells at the back of your eye. All else being equal, smaller images mean smaller things. Here, I'm in no danger of hitting my head on the ceiling. But over here, I am ducking. Ceilings are useful visual landmarks for judging size. Of course, you're making these size estimates based on the assumption that this room is ordinary and box-shaped. You assume the back wall is perpendicular to the line of sight, so the two versions of me are the same distance away. You're also assuming that the floor and ceiling are level and parallel. But as you probably guessed, this isn't the case, and the room isn't box-shaped at all. It's trapezoidal. The back left corner of the room is much farther away than the right. Since I'm farther away over here, my image is smaller, although I'm definitely not. The ceiling cue is also misleading. The floor actually slants upward and the ceiling downward, from left to right, making my head much closer to the ceiling when I'm over here. Why couldn't you see these things and adjust your size estimates? The room's features have been cleverly distorted to be consistent with a rectangular shape. The checkerboard pattern on the floor gets finer grained toward the right, so that the same number of pattern elements fit in a shorter distance. The windows are resized and shaped to match the trapezoidal back wall. Your narrow angle of view from the front of the room blocks the cues that would reveal the room's true shape. And of course, we easily believe in a box shape because that's the shape rooms normally are. This clever setup is called the Ames illusion. American ophthalmologist Adelbert Ames Jr. devised it in 1934 and built a physical example the following year. For Scientific American's instant...
All right, so again, right, on the left side, right, we're going to take our retinal image, right, which is slightly smaller because this is a further away point because of the shape of the room than this. Right? And our perceived depth, though, is staying the same. We're like, hey, if I'm here and I'm over here, my depth hasn't changed because this is a flat wall, right? So if depth doesn't change, but the retinal image does, right, then our perceived image becomes 15 for this, 25 for that, which is why this person looks so much bigger to us than this person. All right. So again, using this equation to understand how these illusions work. All right. Last 15 minutes. This is where things get a little harder. All right. So when we have 2 points out in space, right, closer an object is and the further away an object is changes where that object is represented on my retina, on each eye. Right? On each eye. This is the binocular disparity that we talked about. Okay? So here, the distance in my left eye between A and D is shorter than the distance between B and A on my right eye because of the different angles that we're seeing. Okay? Our retina, we can detect as small as 1 millimeter difference, 1 micrometer difference, right? And this helps us with that depth perception. Our brain is doing a calculation, right? And if I were to move point B up to be equal with point A, to be the same depth, right? Now, the distance in each eye are going to be the same. That tells me that B and A are at the same place, same depth. When that distance isn't the same, it means that one object is closer than the other. So when I move it up, B actually moves over, and now the distance between A and B is identical because they're in the same plane. All right. The blue line here is not a straight plane. Why? Actually, this blue line is not a straight line. Are these lines straight down here? Or are they curved? Curved, why? Because your retina is curved. Right? And because our retina is curved, this plane out here actually becomes curved like this. Actually becomes curved like this. And we call that line the horopter. And it is a hemicircle of our plane of focus. This means that when the lifeguard's looking at Ralph, Susan and Harry are both in focus because they're in the horopter, whereas Carol and Charlie are out of focus because they're in a different plane of view. So when things are on our horopter, they are falling on corresponding retinal points, and we have zero binocular disparity. And that makes the images in focus, and we see a single image. And the horopter is not like a straight line like it's shown, a single flat line like it's shown here. It's actually a region. There's a region of fused images where anything in this region is close enough to the corresponding retinal points that we have no binocular disparity and we see one of them. What happens if we have binocular disparity? What if it falls on non-corresponding retinal points? What do you think your perception is? Yeah. So again, fingers up, right finger close to your nose, left finger far away. Look at your left finger far away. How many of your right finger do you see? Without looking at your right finger, if you look at your far away one, how many do you see? 2. Now look at your close finger. How many of your other finger do you see if you look at the close one? 2, right? You're changing where your horopter is. When things are not in that fused area, we see 2 of them. We have double vision because they're not falling on corresponding retinal points. They're falling on non-corresponding retinal points, and they don't meet up in our LGN. They don't come together. They don't converge, right? Only corresponding retinal points meet up to become a fused image. All right. So how do we, and here's the other tricky part. We can move our horopter, just like you just did, with convergence and accommodation. We can change it where our horopter is close to us or if it's far away. Okay. Again, we get diplopia or double vision when we have things that are not on corresponding retinal points, like you just demonstrated with your fingers, seeing 2 of the finger you weren't focusing on. All right. So when we have things on the horopter, they are falling on corresponding retinal points. So we're going to say that the blue dot is falling on point B in the left eye, and it's falling on B prime, corresponding retinal point over here. So these are all called prime letters, these are all regular letters, right? And we have F is falling on, the red is falling on F, and F prime. We see those as one image because this place in the left eye meets up with this place in the right eye in our LGN. That's how they come together. Now, A is not in our horopter. Green is falling on A here, but it's not falling on A prime here, it's falling on another place. This D prime meets up with D over here, but not with A. And so this signal, the green thing in A is going to a different place in our LGN than D prime is. They don't meet up in the LGN, so we see 2 of these, just like you see 2 of your finger when it's far away. Because it's falling on non-corresponding retinal points. Same thing for things up close. Don't fall on corresponding retinal points. This part of the retina is not hardwired to match up with this part. We can resolve that by converging and accommodating and moving our horopter to this plane. And now this will fall on corresponding retinal points, but none of these will. Does that make sense? I know this is complicated. All right. This is Bob and his magic floating crayons. It's an example from your book, right? And here, the red crayon is on the horopter, the blue crayon is on the horopter. The other two are not. The other two are not. The brown, is it closer or further away to our horopter than the purple? Closer. So if we measure the distance here, right, on our retina, and we compare it to the distance here, right, there's a disparity. It's not the same distance, right? If we measure the distance here between blue and red, and here between blue and red, it's the same. They're falling on the same corresponding points because they're in the horopter. What about purple? Is the distance between purple and red a bigger change than the brown? Yes, and so that tells us the bigger this disparity, the further away from our horopter something is. Let's do this again. I told you what I'm going to do last time you did it. Right? All right, so look at your close finger, okay? And start to bring your far finger in closer. What's happening? The disparity gets less and less and less until you reach that fused region, and you now see one finger instead of two. You're shrinking the binocular disparity the closer you get to that plane of vision. All right. So if we compare, right, here's the difference between our left and right eye, not a whole lot, a very small disparity. That means I'm really close to my horopter. A big disparity, that means I'm really far away. Big disparity, the two fingers are really far away. As we make it smaller, the fingers come together closer until they become in that fused area. All right. So that difference in binocular disparity is a cue, a very complex cue to our brain as to how far away is something. And the thing that's crazy is that this isn't fixed, right? We can move it in space based on accommodation and convergence. You're beginning to see why it would be really hard to create human-like vision in a computer. There's all these things going on. First, you need a binocular computer, and the computer would have to be able to move the lenses and have those signals in order to change the horopter. Those of you that have ever had like a camera with a lens that you focus, right? If you're focusing on something far away or up close, you have to physically move that lens in or out, right? That's what we're doing with our eyes as we change that point of focus. Okay, so not only does the amount of disparity tell us how far away something is from our horopter, how far away it is from our plane of focus, but we can also have another cue that tells us, is it in between us and the horopter, or is it past the horopter? We can actually know on which side of the horopter that thing is. Okay? And this is called crossed and uncrossed disparity. So, cross disparity means that something is in front of our horopter, and that image is going to appear on the nasal side of the thing that's in focus. The thing that's in focus. Something that's further away is going to appear on the peripheral side, and that's called uncrossed. So the distance here, right, is telling us how far away I am, but whether the image is crossed, meaning on the inside parts, or uncrossed on the outside parts, right, it's going to tell us if it's closer or further away from our horopter. And if you were to measure like the amount of disparity here and the amount of disparity here, it's the same because these are the same distance apart. What's changing is crossed to uncrossed based on where my horopter is. I think this is another way to look at this, right? So if I'm on the red point, right, here, I have my cross disparity. This point is a lot closer than the green. I mean, this distance is more than this distance. So the amount of disparity from red is much bigger. The disparity from red to green is much smaller, and it's on the other side. That tells me that this thing is a lot closer than this thing, and it's behind my horopter. And here's the thing. We're able to really quickly change our horopter from back here to up here, and in doing so, how these other images change going from crossed to uncrossed and the amount of disparity, again, tells me where everything is relative to other things. Relative to one another. All right. Much of what we know about this is psychophysical instead of physiological. What does that mean? Yeah, it means if I have you put your fingers out there, right, we're not looking at any neural signals, we're doing all perception and figuring out, okay, that's crossed, that's uncrossed. That's zero disparity because there's one image fused. Right? It's a lot different. It's much more difficult to measure how our brain's interpreting these signals. We know these signals are coming out of the retina, but how our brain is dealing with them is really complex. It's really complex. We do know that there's some symbol cells in the cortex that respond to disparity, that are cued not just for angles of lines, but for how much disparity there are from images on our retina. There are cells that are zero disparity. That means we're in our horopter. The bigger the disparity, again, the further away we are from our plane of focus. Yes?
The horopter, is that just like the exact like this? Is that what our focus is on?
Yes.
So like when you're doing this and you're looking here, that's where your horopter is.
Yeah.
When you're looking here, this
You have converged your eyes and moved the horopter up closer so that now your fused plane of focus is on the finger closest to you and you only see one.
So if I'm looking at this finger, would this be cross?
Yes.
And if I look at this finger, this would be cross.
Uncrossed. Yes. So, we're almost done.
My bad.
All right, I guess that's our cue. I'll pick up here. Actually, I have like a handful of slides. I'll cover that real quick at the start of lab today so we don't get behind because the lab instructions will be pretty short and sweet when we got here. Okay? All right, I'll see you today at 2:30.